Hi, good afternoon. Thank you all for coming. Our research project is using machine learning to correlate Twitter data and weather patterns. I'm Dogariu.
I'm Ashley Cox.
I'm Shruti Garg.
I'm Brandon Khadan.
I'm Michael Scornavacca.
So the main purpose of our research project is firstly to be able to train machine learning models to take Twitter data, text data as inputs, and be able to infer about the weather type from the location which it was posted from. But in a much broader sense, what we're doing is we're comparing how different machine learning models can perform at this particular task.
So now we're going to talk about some of the models that we used as well as the algorithms that we applied along with them. So the first model that we used is known as naive Bayes. This is a purely mathematical approach to machine learning. And this is at the core of naive Bayes is Bayes' theorem, which relates the probability of an event occurring to evidence. And this is the mathematical representation of that. One of the assumptions that Bayes makes is that all the attributes related to an event are independent and affect the conditional probability equally. The actual take that we're doing on naive Bayes is called the Gaussian model. We're going to make a standard distribution of all the possible probabilities, and using that, we can hopefully improve the accuracy of this algorithm.
So the second kind of machine learning algorithm that we use is a multi-layer perceptron. So it's a type of neural network, and what a neural network is it's a structure of interconnected nodes, also known as neurons, that make up different layers, as seen in the picture. And the connections between nodes of different layers each has a weight, and that weight is the strength of the connection. And each individual node has a bias, which is the network's preference towards choosing that node. And these weights and biases are used in something called an activation function to determine what the output of a specific neuron will be. And all these outputs of each neuron come together to make up the output of the network as a whole. And that output is fed into a cost function, which calculates the error of the network by comparing the output that the network gave to the output that the network should have given. And to optimize the algorithm, you need to minimize the cost function, which is done using gradient descent, which uses direction to show how weights and biases should be shifted in order to minimize the cost function.
Okay, the next type of machine learning model that we applied is a convolutional network. So the main difference between a convolutional network and a multi-layer perceptron is that convolutional networks use what are called sliding windows to be able to analyze and detect, to analyze data from different points and retain some sort of spatial context. And this is done across your entire input data, which can be multiple dimensions, which is an advantage of it. And it uses shared weights and biases to generate what is called a feature map. And this feature information is passed through what are called pooling layers, which only pass forward the most important feature information, which lowers the amount of parameters and makes training easier and more efficient. In the picture is depicted a typical convolutional network.
So our final type of neural network is a recurrent network. So we're going to look at multi-layer perceptron really quickly again. All the data goes forward through the network. So with any given layer, the data never travels backward, it only feeds forward. So that's where a recurrent network comes in, where data can actually travel backwards through the network. This is great for text analysis. This actually gives you a sense of context and memory in order to gain the actual meaning of each word. However, one problem with a simple RNNs is that as you reach the end of a sequence, you tend to forget the beginning of the sequence, the beginning of a sentence in this case. That's where we use LSTM, which stands for long short-term memory. So it actually can connect the beginning of a sentence to the end of a sentence. And depicted here is a typical structure for a simple recurrent neural network.
So those were all the machine learning algorithms we used in this project. We also used natural language processing. What natural language processing is, it is a method from which a computer can understand human languages like English, which is really important to this project because we are, in a sense, taking tweets that are written in English, and the computer needs to understand and process them in order to be able to predict the weather. We use sentiment analysis in this project, and sentiment analysis basically understands the emotion behind a text. There's sentiment polarity, which is basically whether a piece of text is neutral, negative, or positive, and there is sentiment intensity, which is how intense is the emotion that the text is expressing. For example, if something is in all uppercase, it is probably more intense than something that is in all lowercase. We also converted words into word vectors, and word vectors are basically numeric representations of words. In the picture, we can see that 2 points each representing a word. The closer they are in meaning, and the closer to numeric representation or word vectors are, the closer those two words are in meaning. We used the GLOVE dataset, which was trained using the Twitter data, so this suits our purposes really well.
So now we're going to get into our research, how we did each algorithm and the results that came from all of them. The first step is to pre-process the data. So that is taking each tweet and pre-processing so it can be inputted into our machine learning models. We had over 228,000 tweets for our data set. We made sure to remove all weather-related tweets. So if a tweet contained a word such as sunny, thunder, rain, clouds, we would make sure to remove it just so it wouldn't bias our machine learning models. We converted all the tweets to lowercase, and we filtered and tagged Twitter-specific tokens. So that is usernames, URLs, and hashtags. A baseline test that we use for our, in order to evaluate the efficiency and accuracy of our machine learning models is the probability, the maximum probability you can achieve solely by guessing. In our case, it's 36.8% because the most common weather type was clear, appearing 36.8% of the time.
So for the naive Bayes algorithm, we actually have to do additional steps for processing the data. Since all of the data has to be numeric values, since we're making graphs out of them, we're going to pass all the tweets through a sentiment analyzer. As we talked about before, this takes the polarity and intensity of each tweet and gives a numeric value between -1 and 1. Additionally, we're going to actually do some standardization and normalization so that we can actually improve the accuracy. This basically just means scaling the values into certain ranges so that they can be compared one-to-one. So now we have the results from the Bayes algorithm. As you can see, we got a testing accuracy of 37.1%. This is 0.3% above our baseline test, so not that much more efficient. And also, as you can see from this graph, the algorithm, although it did guess clear and cloud properly for the most part, it could not establish a correlation between rain and thunderstorm weather types. One of the limitations that makes Bayes kind of inefficient for this type of problem is that naive assumption that basically says that all attributes for each class are independent from each other. In this case, that assumption does not hold, and so as you can see here, the Bayes algorithm does not perform efficiently.
So we built two types of multilayer perceptrons in this project. The first type of multilayer perceptrons took as an input sentiment values of tweets. So before we put data into our perceptron, we needed to process it further. So we took the pre-processed data and removed all the tags from it, and all words that were tagged all caps were changed into all caps, so it looks more like English. And then these tweets were processed through sentiment analyzer, which outputted sentiment values, and groups of sentiment values were inputted into the network structure. So the input layer had 5 nodes, one for each tweet's sentiment value. It had 2 hidden layers, which are basically layers between the input and the output layer, which had 64 and 32 nodes each, and we had 1 output layer with 4 nodes, one for each weather, clear, clouds, rain, and thunderstorms. So the graph on the left shows the results, and as you can see, the results are around 36%, which basically shows that the network did not really find a correlation. What it was in fact doing was it was guessing clear for everything to maximize its accuracy. The red line shows training accuracy, and the blue line shows validation accuracy. Training accuracy is the accuracy during training data, which is data that the machine is learning from and the network is learning from, and validation accuracy is the accuracy from validation data, which is the data it hasn't seen before. And the red line is higher, the training accuracy is higher than the validation accuracy, which is an example of overfitting. where our network was simply memorizing the training data and could not generalize as well to the validation data.
So for the second multilayer perceptron, we used sentence vectors as our input. So first the tweets all had to be converted into sentence vectors from the normal tweets. And then our input layer, we had an input layer and an output layer and 2 hidden layers. And the data was broken up so that 85% of it was used for training and the other 15% was used for validation. So our results for the second multilayer perceptron, we've reached a maximum validation accuracy of 34.5%, which is below the baseline test of guessing all clear. So this network did not perform very well. And the maximum training accuracy was 48.93%, which is much higher than the validation accuracy, which shows that the network was overfitting like the previous multilayer perceptron. And some problems with multilayer perceptrons is that because of the way they're structured, one specific node isn't aware of its connection to the nodes around it, so they aren't able to perform as well as some of the other networks.
In order to apply the convolutional network to its fullest capabilities and to take advantage of the fact that it can analyze data in multiple dimensions, we inputted groups of tweets as opposed to individual tweets. We actually inputted the vectorized form of tweets, the list of numbers, which was made by the average of the component word vectors calculated using the GLOVE dataset, as was mentioned before. And there were some hyperparameters that needed to be optimized in order to gain maximum efficiency, such as the number of tweets per input. 40 was determined to be the best for this particular network, and activation function, the function that it uses with the weights and biases to calculate the output of the neuron. The architecture of the network was a convolutional layer, that's the one with the sliding window that finds feature information, followed by a pooling layer, that's the one that only passes forward the most important feature information. That was repeated twice, and then it was flattened into 2 dense layers, which function similarly to how multi-layer perceptron layers work, and with the last layer being the output layer. As you can see in the graph, where green is the training data accuracy and the blue is the validation accuracy, it reached a maximum validation accuracy of 58.1%, which is over 20% above the baseline. It is also apparent that it is overfitting very heavily, almost fully memorizing the training data, yet it can still generalize relatively well to new data that it has not yet seen.
So our final type of network, the recurrent network, very similar to the convolutional network, we combine tweets into groups. Rather than using an array, we concatenated the tweets, so that is taking each tweet and combining them into one large text block. We optimized the same hyperparameter, the number of tweets per input, and our network architecture had an embedding layer, which essentially takes that text block that I talked about earlier into that word vectors from the GLOVE data set. We had an LSTM layer, and then our dense layer, which had 4 nodes, 1 for each output. So our RNN results, we had a maximum validation accuracy of 65.7%. So that's above the guessing baseline by almost 30%. 32 tweets per input performed the best according to our tests. And we didn't have barely any overfitting until about epoch 100, where it started to slightly go above the validation accuracy. So our conclusion, what does this all mean together? Again, the highest accuracy was with the RNN, mainly because of the structural advantages. As I mentioned earlier, the text analysis, the memory, the LSTMs, helps it perform very well with these tweets. Group data performs much better than individual tweets, simply because there's more context to pull from, more information to grab from those text blocks. So why is this important? What does this all mean put together? Well, we removed all weather words, so there was no information about weather in these tweets. The neural network figured that out for itself. We were able to discover a correlation between something that had no information about our subject. So this kind of proves that there could be a correlation between any real-world phenomena and social media posts.
Yeah, just to reiterate our goals, we did a comparative analysis of these algorithms to see which would be most efficient at solving this problem of finding the weather based on user sentiment in tweets. And given that our accuracy was 65%, we did find a correlation. though there are some issues that we want to work out in the future if we continue this research. Namely, automated posting systems. In our data set, there are actually machines that have just posted tweets. They're not actually people, so measuring the sentiment value there is useless. So that just adds error into our prediction models. Also, we only pooled information from one location, and that's just Twitter. This was due to the fact of many restrictions on where we could get our information from. But in the future, we hopefully can pull from a broader data set and hopefully find if these correlations hold throughout different locations. And lastly, we want to actually apply more complex algorithms, namely convolutional recurrent neural networks, combining the two most efficient algorithms and seeing if this combination makes a more efficient algorithm.
So we would like to thank all of these people who have made it possible for this for us to do this research. We would like to thank Benjamin Lee, Sachin Matthew, Dean John Patrick Antoine, Helen Sages, Michael Higgins, New Jersey Space Grant Consortium, Lockheed Martin, New Jersey Governors School of Engineering and Technology alumni, Rutgers School of Engineering, and the Rutgers University. Thank you all. These are our references. Thank you all for listening.
Could you please go into more detail about gradient descent?
We have an additional slide depicting gradient descent. So, what gradient descent does is it uses the gradient, which for those of you who are familiar with calculus is it's a form of a derivative in multivariable calculus. It's the direction of the steepest descent of our cost function in this case. So what we do is the gradient descent is a vector of partial derivatives, this is getting technical, that basically encapsulates information about which directions and how much the weights and biases in our networks need to change in order to minimize the cost function, because that's the goal of this. And in order to actually, calculate or in some cases approximate the gradient, backpropagation is used, which is a technique that uses multivariable chain rule to work backwards through the network. And depicted there is a very beautiful animation of how gradient descent would take steps in the direction of the negative gradient to minimize the cost function.
This picture represents a gradient descent with only two variables, that being x and y, and z being the cost function. The goal is to minimize z, which is the cost or the error in our network. Again, you would have more than two variables, so that would be thousands or tens of thousands. This would eventually turn into like a 10,000 dimensional graph, which is why you need linear algebra and multivariable calculus in order to calculate questions.
What machine learning framework did you use? Is it TensorFlow and Keras?
Yes.
Yes.
TensorFlow and Keras.
And
As
what
well
environment
as
did you
scikit-learn.
run?
I'm sorry?
Where did you run that environment? How you trained the model?
We trained it on my own personal desktop. We use AWS or Google Cloud or anything. They were relatively easy to train. It only took about 6 hours for the max for the recurrent neural network. So.
Since tweets about weather seem to be a natural occurrence, why did you decide to take the weather tweets out? And how would the model have performed as you left the weather tweets in? Did you do that?
So we have a graph.
We have another graph. So this is our training validation accuracy for the recurrent neural network. So this is the one that was the most accurate without the weather words. We trained it again, including weather words. That is sun, thunder, rain, storm. It actually reached a maximum validation accuracy of 76%, which is considerably higher than the one without weather words. So we were able to derive even more information from the fact that these weather words existed, which says something in and of itself.
Yeah, a large purpose of our project was to demonstrate that we can also derive weather information while excluding this weather data set, because otherwise it would be a lot easier for machine learning models to perform that.
So it sounds like you excluded nouns but adjectives like human or cool.
So we had a list of about 25 words that were excluded, and some of those were in fact adjectives. Most of them were specific weather words, such as rain and thunder and all of those. But for future research, we would like to make a comprehensive list. One of the problems with excluding those words, however, is they are almost essential to kind of using our sentiment analysis or for relating some of the words in our word vector space. So we're not entirely sure how that would affect the accuracy, but that would be definitely something we'd like to do future research on.
What is the rationale for using weather as
Honestly, so Twitter was the easiest way to get data. So weather was something just for us, from our perspective, it was something that you couldn't normally see by looking at a group of tweets, whether it was raining or thundering or just cloudy. So we thought it would be an interesting thing to throw into some of these deep neural networks in order to derive some of that correlation that we normally couldn't see just by looking at the tweets. So if there was any specific reason why we chose that, I think it was just our personal preference.
Thank you, fellas.